Okay, great. So thanks for joining us today. We're going to be doing chemistry, biochemistry in anatomy class. We just finished doing atoms, elements, and some bonding, polarity, and why things want to react, sharing of electrons and stuff like that. So we're going to do inorganic molecules right now. Next time we'll do organic molecules. Okay. And first big molecule in your body that is not considered inorganic is water. So we're going to talk about water first. First of all, what is an inorganic molecule? Like what makes it inorganic? All right, it's not because it's using too many pesticides or something like that. That's more of a definition of organic farming would be like less pesticides, less things that are harmful. Because the irony is in a chemistry lab, a lot of those pesticides and chemicals and herbicides and stuff like that are actually organic molecules. They're just poisonous to humans. And so, yeah, um, it's a different definition. So, what is inorganic? Any molecules that are small, pretty much that's it. Like, usually not non-carbon chains. All right. So, no carbon or non-carbon chain, no carbon chains. All right. That one's kind of hard, usually. I think methane is still considered a organic molecule. But that's okay. So we're going to talk about inorganic. We're going to talk about water. It's small. It makes up to, let's say, 31 to 79% of your body. People disagree on that, like how much of your body actually forms water when it breaks down after it's decomposing. Well, it's a lot. So we're just saying we're very watery, okay? So we're very watery, anyways, decomposing or no. Let's say 60% average. It's essential to your body, though. Water is essential to life for many reasons. It's the universal solvent, is one. It transports substances throughout the body, like salts. They dissolve in H2O, or AKA water. And they're going to form ions. They're going to form ions depending on the salt. They're going to break apart. We call it dissociate. They don't just dissolve, they don't just fit well in water so that you can't tell if it's a mixture or not. They actually break apart. So sodium chloride might break apart into like Na plus. Chlorine would be its negative one ion, right? Potassium will break apart into its ion. Maybe you have some iodine. Um, but yeah, you're gonna have all kinds of salts in your body, calcium and like ions. They're gonna break apart, okay, to their elemental like ion form. These are going to be considered aqueous solutions. That means they're in water. All right, that agua is comes from the Latin. Okay, these solutions they transport stuff. Okay, that's pretty general. What kind of stuff are they transporting? Well, let's say nutrients, um, red blood cells. Yeah, let's say cells, right? Cells that wander, white blood cells, red blood cells, and waste. Of course, got to get rid of the waste, right? That's pretty broad. What are we talking about? We're talking about the nutrients. Well, just it allows us to eat. All right, we need to eat. We need to maintain homeostasis. One of those is pH, right? We're going to talk about that too. We're going to talk about acids. They're a type of inorganic molecule. And for nutrients, though, you don't just include like things that you eat. You're also thinking of things that you breathe, like gases, like O2. Waste, CO2. Yeah, you got to carry that away. And that's going to happen in your blood too, mostly in your plasma, actually. And maybe your red blood cells carry the oxygen. So we got to transport stuff. So it's good that water is the universal solvent so that things can dissolve, maybe dissociate, and then be transported in the blood usually. All right. Water is a lubricant and a shock absorber. That's another thing that's really important about water. It's going to help prevent abrasion, just like injury from friction. Where surfaces meet, like lungs, for example. When your lungs are breathing in and they're kind of rubbing against the membrane and the cavity that the lungs are in, the pleural cavity. Your heart, it's got to be able to beat any kind of muscles flexing through joints too. They got to be able to move, and they have like synovial joints have fluid capsules. Maybe your eyes need it to be able to move around and be able to see in your eyes. You might have vitreous fluid, so you're gonna have fluid in your eyes too. And then I guess there's in your mouth. In your lungs is, I guess you have some serous fluid. Seriously? Yeah. Oh, now I spelled it wrong because I was saying seriously. Okay, serous fluid without the I. Also, it's the basis of your cerebral spinal fluid that you're going to need to keep your brain bathed with fluids and your spine. Did you know your brain is floating in waters, in cerebral spinal fluid? Yeah, if it didn't, it'd be rubbing against the bone underneath it and you get brain damaged literally from like shaking your head, right? So we got to keep that cushioned, but also nutrients are flowing through that cerebral spinal fluid and waste is being taken away because you don't have a lot of blood vessels don't directly feed into your brain cells and your nerves there. Also, as a baby, you're going to need amniotic fluid. Yeah. Do you know where that comes from? That's so the baby, delicate tissues can develop and be floating around, kind of rocking in the and swaying in the fluid. Yeah, it's the baby's urine. Um, Developing fetus. Yeah, that's it. That's where it comes from. The mama doesn't make it. The baby does because the baby's got to, have those kidneys cleaning out the body too. So water is a lubricant and a shock absorber, but it also has a high heat capacity. In other words, it takes a lot of energy for it to change temperature, at least compared to other molecules that are similar to water. So it changes temperature slowly. Thank goodness for our Earth, too, because it keeps us from having temperature extremes during the night and the day. So water can absorb heat, and then it also can store it and then releases it slowly to avoid extreme temperature changes. Also, yeah, just saying absorbs a lot of heat. There we go. This helps to maintain normal body temperature. And also water, it takes a bit of energy for it to boil and turn into gases too. So we're thankful for that. That has to do with the water's polarity, which we talked about a little bit about. The hydrogen bonds, water kind of likes itself. It likes each other. Yay. So that it takes a bit more energy for it to get over those bonds and turn into gas. Water is needed for chemical reactions in their body. All of your chemical reactions in your body occur in water, aqueous solutions. And water is continuously flowing. It has to in and out of cells and vessels. And water in different places in your body is going to be called different things. Okay, sorry, that's kind of in the way, huh? When it's around, or sorry, yeah, let's say it's inside the cells. Let's say intracellular. It's an intracellular fluid. It's inside cells. It's kind of like your intranet. Like that's an intranet is between people of the same company, maybe in the same building, and you guys share data and information just that way. AKA the cytosol. Extracellular fluid are outside of cells. And some of these outside of cell places could be in your blood vessels. If it's in your blood vessels, it's called plasma. So it's in vessels, not the red blood cells and the white blood cells. Just saying the watery part. Okay. In the lymph, those are, by the way, vessels that are also carrying fluids, usually from the extremities towards your heart, and they kind of collect and they go past lymph nodes. They clean your system out. It's a whole system of vessels. They don't have a heart rate. You don't have their own little heart. They're just relying on pressure and squeezing your muscles because the lymph vessels go through your muscles. But yeah, it also activates your immune system. It goes by your lymph nodes and it helps clean out tissue around the cells. So in lymph vessels, it's going to be called lymph, and in lymph nodes. Yeah. Tissue fluid that is just outside of cells and in no other special place is called interstitial fluid. And another name for that is intercellular. That's like the internet. So it's not inside the cells, it's outside of the cells, so it's connecting cells to cells, okay? So think of it like as the internet connects like one business to another to like the whole rest of the world. So it's still, it's not in the plasma, it's not in the lymph, but it's just outside of the cells and it's called intercellular fluid, all right? AKA around cells. So you can kind of say that these guys are related. Intracellular and extra and intracellular and intercellular. Okay, cool. Specialized fluids, those are things like you secrete, maybe. Let's say blood, sweat, and tears. Well, we already got blood. So sweat, tears, anything you produce, mucus, urine, saliva. I guess any digestive juices. Saliva is the beginning of digestion, right? You start breaking down your starches in your mouth, stomach acid, stuff like that. Ooh, bile, maybe. Bile is kind of a digestive juice, so it's all in there. So yeah, that's the water that's in your body and where and what it's called and what it kind of does. So going on to some inorganic molecules, you do need to talk about oxygen because oxygen is super important for cellular respiration, right? Remember that formula maybe back in bio? Glucose takes oxygen to break it down into its waste products, CO2 plus H2O. And of course, you produce energy. We'll just say energy. Mostly ATP, but that has to happen in many steps. Let's balance this equation. It's 666 to balance it. Yeah. Yeah. Oxygen is one of those covalent compounds we kind of talked about. And it's going to, here, let's just say oxygen. Its electrons can share with each other. So oxygen's never by itself. It's always O2. And let me draw these a little bit different. Here's its 6 electrons. 2 are unpaired. It wants 2 more to have a complete outer valence shell. So it shares its 1 available electron with the other oxygen, and that other oxygen shares its 1 available electron there, and then it does it twice, so it's a double bond. So that's why oxygen's happy by itself. And another way to write it is that. So it's a sharing bond and it's a covalent. Let's just sort of write that a different, okay? And it's covalent molecule or element. It's pure. It's not a compound because there's only oxygen in it. All right, just letting you know. We talked about compounds, more than one element, more than one element type. Oxygen is just oxygen. Okay, now CO2 has 1 carbon and 2 oxygens, and I showed you the formula a little bit of that earlier. It's the waste product of cellular respiration. But as you'll see in a bit, we use it as a buffer in your blood too. It makes your blood a little acidic, but your body can deal with it and then uses it to make it kind of a buffer. That's a compound, right? Carbon dioxide, definitely a compound. CO2, two oxygens, one carbon. I'm just going to give you the valence electron diagram, the Lewis dot diagrams of carbon. That's the outer shells for, so no circles. And oxygen, let's do, I guess we like to do north, south, east, west. There's at 6. Let's do this. Okay, so carbon shares 2 with oxygen. Oxygen shares 2 back. Then carbon shares other 2 with oxygen, and oxygen shares its 2 back. So it's literally it has 2 double bonds. All right, this would be how it would be more like. Sometimes you can abbreviate it like that. Okay, so the other thing that we talked about that are inorganic molecules in your body are all the trace elements that we talked about. That is anything but the big 5. Kind of, for example, let's see if I have a good one. Calcium and phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, iron, fluoride, any of these elements that are not the big 5, oxygen, carbon, hydrogen, nitrogen, those are going to combine to make your organic molecules. The inorganics start down here with calcium, and you're going to even end with like trace elements that you've barely heard about. I mean, there's zinc, of course, and then you need manganese, copper. Yep, it's in your body too. Selenium, cobalt, arsenic, chromium, lithium, and molybdenum. Yeah, you need that. I know. Others too. Of the 92 naturally occurring elements, you need most of them in your body. Interesting, huh? Even stuff that would be considered poisonous. So we talked about those already on your front page. The next type of inorganic molecule we're going to talk about are acids and bases. Sorry, this printed out weird. Acids and bases. They are ionic compounds. So they have a cation and anion. But they're going to release hydrogen cation or hydroxide anion into the solution, or they're going to bind hydrogen. Maybe they remove it from a solution. So if it contributes to an increase of hydrogen, then it's going to be acid, which I'm going to write in red because our indicator is usually red in the presence of an acid. And if OH concentrations get increased, it's because it's a base. All right, maybe a base lowered the hydrogen ion concentration. So that's what it could. And we'll talk about that. All right, so acids, pH are less than 7. We'll learn what pH is in a second. For example, hydrochloric acid, the hydrogen is a cation, the chlorine is the anion, and when they get into water, they dissociate into their ions, chlorine and hydrogen, and that's what's going to make it an acid. Okay, so pH is less than 7 for an acidic compound. Okay, for bases, pH is greater than 7. I can't, for some reason I just write P instead of pH. I don't know why. pH is greater than 7. And for example, one base would be sodium hydroxide. And in water, it's going to dissociate into sodium and its hydroxide ion. Yeah, you could have ions that are sets of molecules that stay together. But this is interesting to water, specific to water, that this would be a base if it releases hydroxide or decreases hydrogen. And I'll explain that. The pH scale, I don't know if you could tell, is right here. And it goes from really 0, I guess, to 14. Okay. And what it is it's the concentration. It's related to the concentration of the hydrogen ion right here. It says concentration of hydrogen ion. But when you do the P of the H, that means power of the hydrogen. It's really the negative of the exponent. So, for example, 10 to the 0. Okay, that's just going to be 1. That would be a pH with a concentration of hydrogen 1 molarity. Okay, with the pH of 1. So pH value is 0, but to pH of 1, that means 1 times 10 to the negative 1. And that means we're going to move it over a decimal. And that's a molarity of 0.1 of just hydrogen ions. pure hydrogen. So that's really acidic. As you can see, it decreases at each level by a tenth. And that's why the pH number, as the pH number grows, the acid concentration actually decreases. So it's a little counterintuitive since you're usually expecting as the number increases for things to increase, but nope. pH is getting towards 7, and 7's where we're neutral. 7 is like maybe pure water. Okay. It all has to do with hydrogen and hydroxide. All right, I'll show you in a second. Just want to show you down here, there is a pH of 14. That's usually what at the end of our scale. So I guess it goes from 0 to 14, indicating whether something's an acid or a base. And another word for base is alkalinity or alkaline. The middle of the scale is 7. Here, I'll do that in black, indicating something that's neutral, a neutral solution. One that is neither an acid nor a base. Why? Why is water neutral? Okay, this is why. Because to make water, actually, if you took a hydrogen ion and a hydroxide ion, and they form water for the most part. Okay, they want to form water. That's neutral. If you decrease the hydrogen ion concentration, then you have more hydroxide. We're non-neutral anymore. We have more hydroxide. We're actually more of a base. If you increase the hydrogen ion, then you have like all the rest of the hydroxide sort of get used up by hydrogen, and there's extra hydrogen, and you have an acidic solution. But when these equal each other, here's chemistry lingo for concentration, these brackets. If the concentration of the hydrogen ion equals the concentration of the hydroxide ion, then that's at neutral, and they 100% make water. Well, that might be an oversimplification, but it does. And at that case, water or hydrogen ion concentration, will see a little bit of it goes back and forth is what I was trying to say. A little bit of it goes back and forth. Sometimes the reactions, they don't just happen one way. They kind of have an equilibrium. Most of it's in water. A little of it kind of goes back and forth. And at neutral, the pH is 7. So the hydrogen ion concentration is 1 times 10 to the negative 7th. So is the hydroxide concentration. And that's kind of as far as we're going to get on that. Because these make like a constant, and you can like figure one out or the other. All right. But what I want to tell you about pH is a change in 1 pH unit is a 10 times change. It's a 10-fold change in hydrogen ions, in acidity. So that stomach acid is right here at a pH of 2, very acidic. Lemon juice, somewhere down closer to vinegar. That's okay. Black coffee, down here at 5. How many pHs do we have to jump here? We'd have to jump 1. Gosh, yeah, cola is pretty acidic. 2, we made 3 jumps. So that was a 10 times 10 times 10 change in the strength of those between those acids. So stomach acid is 1,000 times stronger than black coffee. Yeah. So just saying that, yeah, it's a big change in the pH. So we need to keep our pH fluids pretty stable. And normally we try to keep our fluids in the cells and internal fluids at a pH of 6.8. So we let it be a little acidic, but ladies and gents, your body is producing all kinds of products that make it want to be acidic. Like they add acid to your system. CO2 is actually acidic, all right, when it's dissolved. And your body also might do protein metabolism and create uric acid that your kidneys need to remove. That's acidic. If you're making lactic acid, because you're not breathing in as much and you're doing a lot of anaerobic respiration, so your body tissues tend to be acidic, and we try to keep it and maintain it from getting too acidic because it can cause damage to your hydrogen ions or hydrogen bonding in your enzymes. Especially, it's going to interrupt chemical reactions, and it's very catastrophic, and it's going to interrupt molecules that are in your body and tear them apart. So you want to keep the pH in a pretty good range, your blood actually is trying to equalize this so it maintains its pH as a little bit basic, between about 7.35 to 7.45. Things are going to change whether you're exercising or not, or, depending on diet, depending on, but that's what it tries to keep things at, about average of 7.4. So a decrease in one pH unit would terribly disrupt chemical reactions in the blood. It's a huge change, and it would cause death to an individual. All right. Normal metabolism seems to make body fluids more acidic. We talked about that. The kidneys are going to try to counteract that because they're going to try to excrete acid, right? The respiratory system, it's going to breathe out CO2. So kidneys are going to excrete whatever you need, but maybe it's going to be the acid, whether it's lactic acid or uric acid or whatever they can. Respiratory system is going to give off CO2. So you got to remember to breathe out if you can. Yeah. And your circulatory systems are going to work to constantly maintain blood pH levels, because your circulatory has its own buffer system. All right. Buffers, they are in the body. And one of them that's a classic is carbonate. We're going to say carbonate. We're going to find out what carbonate. Well, carbonate's some acid, apparently. So carbonate is just, this reaction is when HCO3, the ion, gets in touch with a little bit of acid, H+, should have made that red. That's positive H+ ions. This is a negative anion. And it's going to form a carbonate of H2CO3. All right. And it's going to try to grab the extra hydrogen until your body can kind of get rid of it. So that's good. That's why it's kind of a base, but it's actually both. It's actually a buffer. It's not a base or an acid. It will bind to hydrogen ions when the body fluid is becoming too acidic, taking hydrogen out of the solution, or it's going to release OH when the solution is too acidic. Oh, I'm sorry. It's binding to hydrogen with fluid, and it's going to release hydrogen. Sorry, when the fluid is too basic. There we go. That's better. Yeah, it just releases that hydrogen. I don't know what I was thinking. It's going to lower the pH in that case, and make things less acidic. These reactions would take place in less than a second whenever acids and bases are formed that would greatly alter the pH. Okay, so that's acids and bases. I'm going to end with salts, but first I'm going to show you just a little quick demo. I took some purple cabbage juice, and yeah, it's sort of purpley. And what the thing is about purple cabbage juice, I hope you can see that, is that it turns red in acid. Okay, let's try it. And it turns blue in base, but if it's really basic, actually it turns green. Yeah, so it's like it goes from a beautiful blue to a teal. It's beautiful. It's purple when about neutral. I made this yesterday, so see the solution getting pinker as things get more acidic as I add lemon juice. Yeah, so lemon juice is an acid. And then, your body system, maybe you've had a lot of acidic foods and you've had a lot of indigestion because your stomach's not digesting and emptying out and repairing itself in the mucus lining. So maybe you have a stomach ache, and maybe to help your stomach ache, you decide to take some antacid. So maybe you take some Tums, and I always forget to grind these up ahead of time so that they actually react faster. Because you'll chew these up. Here, yeah, I'll just try to do that. And yeah, I need to mash these up real good, because they're not going to dissolve super quickly. Like if they're in stomach acid, they're going to dissolve really quickly, and it's just going to lower the pink in here. Make it a little less pink. Make it more purple. I don't know if you can see that from where you're at, but yeah, making it a little bit less pink. It's more purpley. So yeah, Tums, calcium bicarbonate or calcium carbonate. Yeah, it's a little bit of base. And let's say you were out and you did not have a chance to get any Tums and your stomach's killing you and you don't want to go to the store. You can eat some of this baking soda. Yeah. And it's just sodium bicarbonate. See, there's that bicarbonate. Oh yeah, this is getting already purpley. Well, we're gonna push it over maybe push over the edge here and get even more basic. So it's blue, usually basic, red acid. But something that's stronger than baking soda as a base would be bleach, and very dangerous if you ingest it because your body tissues would get kind of tore apart because we're used to being very acidic. So you can see it's going to turn it a little more, even more basic, like a teal colored. And then if I add a little bit more, it's going to be green. Yeah, this is greener looking. Okay. Yeah, that purple cabbage juice is fun to play with. At home, it's fun. If you're stuck at home and you want a little chemistry experiment, just chop up a bunch of purple cabbage juice or purple cabbage and then put some water with it and just heat it on the stove. Don't heat it too long. I always make that mistake and boil it. You don't really need to boil it. Just need to extract a little bit out of it and then strain the cabbage out. And voila. This is vinegar. It's an acid. Yeah, acetic acid. Your body tends to be a little bit acidic. So if it's stuff that you want to test, you got to compare it to the normal purple cabbage juice color that you have. If you let purple cabbage juice sit around, by the way, not only does it smell because it has similar chemicals to sewage, but it oxidizes and it doesn't stay true to its color. Let's see. I think we decided that this guy over here, soap is usually basic. The problem is you can't test it unless it's clear. And this stuff's the clear stuff I could get, but as far as I know, it's pH balanced. So, because it's hand soap, they don't always pH balance liquid soap. So, like for dishes. So I'm trying to see if maybe it'll get a little blue. It looks like a little bluer to me. Okay, because it was purpley. So yeah, soap is usually a little bit of a base, but that's okay. All right, so yeah, I'm seeing some color change. Alcohols are a little bit acidic too, and it's just a very subtle color though. You need really small glasses and small amounts so you can get the light to go through it to really see it. Milk of magnesia. You're gonna take that. Not only do the magnesium help keep things through, but it's a base. A lot of minerals are bases there, like the Great Salt Lakes. Yeah, basic there, very basic. Geez, seawater, by the way, pH of 8, very similar to blood. Yeah, they think life on Earth started in water. So, and then they think that seawater just got more and more salty and more minerals in it and got more and more basic over the years and years. Oven cleaner, nasty stuff. And sodium hydroxide, super basic. So if you were talking about the chemical that maybe Batman accidentally pushed Joker into, it wouldn't have been a vat of acid, it would have been a vat of base, because that's more dangerous and that would rip apart, our tissue. Our tissue is not able to handle that because we're used to being a little bit basic or a little bit acidic in our tissue. So yeah, your stomach acid, very acidic. Pure hydrochloric acid, though, is more acidic than that even. So, and that's why your stomach has its lining, its mucus lining to protect it. Okay, the last thing we're talking about are salts. In general, salts are just ionic compounds made of a positive ion other than hydrogen. So it's any kind of positive ion other than hydrogen and a negative ion other than OH. When salts dissolve in the body water solution, the body will form the cations that are positive. I guess I always put cations as blue. Yeah, that's okay. Doesn't matter. Kitty cat ions, they're positive. Remember the kitty cat plus sign, right? Cation here is like whiskers of a cat. And cats are positive. They have paws and they're positive. The negative are anions. Okay, so the opposite, like the antagonist. And they're anything negative. We need them. We need salts to be available and dissociate so that we can use them for functions in our body, chemical functions. We need it for muscle contraction. Just basic, all the time muscle contractions. Transmission of nerves. We need these polar molecules to polarize and depolarize and repolarize. We need a good electrolyte balance so we can hang on to our water. Otherwise, you lose your water. You pee it right out. So you need enough saltiness to hang on to your water and to stay watery. And then we need minerals and other salty ions, really, to strengthen bones and teeth. Phosphorus, fluoride. We kind of studied a little bit about that. I guess phosphorus is usually in PO4, but it could be an ion, I guess. Phosphate could be, and fluoride, maybe sodium fluoride, maybe what you brush your teeth with. You a lot of times, remember, you have sodium chloride is table salt. That's a salt, right? You need the chlorine to make hydrochloric acid in your stomach. And sodium and chlorine also like balances out other positive cations, which we'll find out later. And the sodium is involved with polarizing and depolarizing for muscle contraction. You also need calcium ions for that, and potassium. Yep. So these are all good. They may be the basis of some of the salts that you might eat, like you might eat potassium chloride, right? In your system, it's going to dissociate. And, calcium in your milk and stuff like that. Okay, so that's going to round out our inorganic molecules. And next time we'll talk about organic molecules. Thank you for staying with us, and I hope you have a lovely evening.